In this video, we present our work, VISION-SLS, Safe Perception-Based Control from Learned Visual Representations via System-Level Synthesis. We consider the problem of safe output feedback control, that is, perception-based control, from high-resolution RGB images. We consider robots with uncertain nonlinear dynamics and uncertain sensor observations. Our goal is to synthesize a causal output feedback policy, PI, that maps the history of observations, Y, to a control input U that keeps the robot within a safe set, S, despite the uncertainties, W, and E. Typically, this requires information gathering, that is, the process of strategically maneuvering the robot to regions of the state space where sensor error is lower, thereby reducing uncertainty and enabling robust constraint satisfaction. As written, this output feedback problem is difficult, as it involves optimization over an infinite dimensional space of causal output feedback policies. To scalably construct the output feedback controller PI, we build upon the system-level synthesis framework, which yields an approximate solution to the idealized output feedback problem, constructing a 1 reference state trajectory, Z, 2, a reference control trajectory, V, and 3, a tracking feedback controller, K, that uses sensor measurements gathered online to robustly stabilize the robot to guarantee safety. In particular, these gains K are derived by post-processing an intermediate decision variable phi, which also defines closed-loop reachable tubes. These reachable tubes can be used as constraint tightenings that define how far the nominal trajectory needs to stay from the constraint boundary, such that the closed-loop system is robustly safe under uncertainty. To reduce the dimensionality of image observations, we use pre-trained visual features, namely Dino V2, and further train a neural network P to map the Dino features to a lower dimension. We train a linear observation function, H sub r, that approximates P given the states of the robot. Notably, P and H sub r are learned so as to maximize the observability of the underlying state X, measured as the size of the minimum singular value of the observability matrix O. A polynomial is then fit to over-approximate the error between P and H, which is used to bound the observation uncertainty in the SLS optimal control problem that arises from learned perception error. Due to the large number of decision variables, naively solving this SLS problem with traditional solvers is extremely inefficient. To overcome this, we design a scalable solver for this problem based on solving 2 parallelized Riccati recursions, one solving for a controller, in step 2b, and one for an estimator, in step 2c. This significantly reduces solve times and makes output feedback SLS practical for robotics problems. These Riccati recursions are a subroutine within a broader sequential convex program, which jointly optimizes the SLS controller variables, phi, with the nominal trajectory Z and V. This fast solver enables the problem to be solved efficiently, either offline or in a receding horizon fashion. The solution is then applied during online execution, using the learned perception function P. In following experiments, we plot the reachable sets of some robot state dimensions as unions of axis-aligned rectangles and compare our method with 3 possible baselines. The rollouts are subjected to identical errors for our method and baselines. In the parking lot experiment, there is an occluded region, and a car needs to navigate to a desired goal region using images from an overhead camera. In the occluded region, the perception accuracy is degraded. The resulting learned perception uncertainty bound is shown as a heat map in the right figure. The CE baseline leads to larger total tube size, and thus accumulates more uncertainty compared to our method. The non-robust baseline collides with an obstacle in some of the rollouts. In contrast, our method plans a non-trivial trajectory, which avoids traversing directly through the occluded region in order to reduce the perception uncertainty. Also, it robustly avoids collision with obstacles, since we explicitly consider the uncertainties during policy optimization. In the quadrotor experiment, the drone needs to navigate through pillars using images captured by its onboard camera. Similar to the parking lot experiment, the CE baseline has a larger total tube size, and the non-robust baseline can lead to safety violations and collisions. In contrast, our method remains safe and accumulates less uncertainty. These 2 experiments show that our method reduces the total size of reachable sets, as well as robustly guarantees safety under uncertainty. In the humanoid backflip experiment, a Unitree G1 humanoid needs to complete a backflip when it only measures its pose and joint angles, and no velocities. This is a challenging high-dimensional benchmark, with 60 states. To show the need for closed-loop control to reject disturbances in our setting, we first plot open-loop rollouts of the resulting reference trajectory. This open-loop controller leads to an unnatural landing pose and can cause large joint angles that may damage the robot. In contrast, our closed-loop controller keeps the system within the reachable tubes and maintains constraint satisfaction. This experiment shows not only the robustness of our method, but also the scalability to high-dimensional state spaces. To the best of our knowledge, our method is the first to synthesize a certified output feedback policy for a system of this dimension. In the hardware experiment, the Turtlebot needs to navigate in an office area with its onboard camera. As shown in the right figure, the rollouts in real-world deployment lie in the computed tubes, which indicates the efficacy of our method and that our theoretical guarantees translate to real-world scenarios. We summarize our approach and contributions as follows. Thank you for listening.